In this segment, we continue our discussion of addition reactions to aldehydes and ketones, where we're adding nucleophiles to the carbonyl group. And in this particular segment, our focus is going to be on adding amines as our nucleophiles to the aldehydes and ketones. And what we're going to see is that by adding amines as our nucleophile to aldehydes and ketones, what we end up yielding as the functional group in our final observed natural product is going to be either the imine functional group or the enamine functional group. So the imine functional group, by definition, is going to have a carbon-nitrogen double bond, like we see here, and then that nitrogen is going to be connected to whatever R group there so that we have our complete octet on the nitrogen atom. That's going to form our imine functional group. The essential parts of that are what I've highlighted there in yellow, that we have to have a carbon-nitrogen double bond. On the other hand, in the enamine, we can kind of dissect here what we're looking at based on the name of it. So ene is going to stand for alkene. Amine stands for our typical amine, a nitrogen bonded to two hydrogens or two carbons or whatever there as our R groups. So our enamine, by definition, is going to have our alkene group, and then one of those two carbons of the alkene group is going to be directly bonded to our nitrogen of the amine group there. So we're going to take a look at how in the world we can add amines as our nucleophiles to aldehydes and ketones and end up with either an imine product or an enamine product. We're going to start by looking at situations that will end up yielding the imine product, that carbon-nitrogen double bond. And those reactions are going to be at play when we have a primary amine reacting with an aldehyde or ketone. So we'll go ahead and write out our general reaction here. So we're writing out the general reaction for forming an imine. And the general reaction that yields an imine is going to involve taking a primary amine, reacting with an aldehyde or ketone, and out of that reaction, we're going to get the corresponding imine, I-M-I-N-E, product that has that carbon-nitrogen double bond. So as a reminder, when we use the term primary amine, what we're referring to as a nitrogen that has just one alkyl group bonded to it. So nitrogen and an R group here, we'll define R as an alkyl group. We'll also see a little bit later that there is some flexibility there about the nature of that group that's bonded there, but we definitely have to have two hydrogen atoms here. So NRH2, those two hydrogens are going to be essential, as we will see in the mechanism a little bit later on. So we'll take that primary amine, react it with an aldehyde or ketone, and get our so-called imine product out of that. On the other hand, the situation that will end up yielding an enamine product is going to be the situation where instead of having a primary amine as our starting material, instead, as our starting material, we're going to begin with a secondary amine. So in general, our secondary amine, where we have our nitrogen directly bonded to two R groups instead of just one R group. So we only have one hydrogen there in that case, because otherwise we'd go over the octet for the nitrogen. So we're going to take a molecule that's just one hydrogen-nitrogen bond, react it with an aldehyde or ketone, and out of that is going to come an enamine. So the main difference we're going to see that drives the formation of an imine versus an enamine is going to be the presence or absence of hydrogen atoms there that are bonded to our nitrogen. We're going to see that we have some loss of those going on as we walk through the mechanism, and that's going to drive whether we're able to form an imine or an enamine product. So primary amines always give imine products, secondary amines always give enamine products. So let's take a look at the mechanism for an example reaction here to see how in the world we go from a primary amine reacting with an aldehyde or ketone to this crazy imine product where we have the carbon-nitrogen bond present there. So we're going to set up this reaction with our aldehyde or ketone. We can take whatever aldehyde or ketone we want here in this example problem. We'll go ahead and start here with a 5-carbon ketone. We'll refer to this as 2-pentanone, of course. And we're going to react it with a primary amine. We can react it with a variety of different molecules, the main thing here is that we have to have an NH2 group present. There's definitely some flexibility there about what the R group is. The R group could even be something like a hydroxy group, so it could have NH2OH, or we could have something more like a prototypical amine, which would be something like, say, H2N, CH3, or methylamine. So we'll typically run this reaction under slightly acidic conditions. Not so acidic that the first step will be protonation, but slightly acidic so that we will have a little bit of an excess of proton later on in order to do a protonation step as we get further into the mechanism. So we're going to have this condition slightly acidic, not so acidic that the favorite first step is protonation, but instead just a little bit acidic, and that's going to allow the first step of this mechanism to be the nucleophile attacking the electrophilic carbon. So this first step of the mechanism, you can think of it as behaving very much like a basic system, really, where the nucleophile is going to attack the electrophilic carbon atom. And that electrophilic carbon is, of course, the carbon atom of that carbonyl group, because it's going to be our very polarized carbon atom, as we've seen as a theme throughout these addition reactions of nucleophiles adding to electrophilic carbonyls. So we'll go ahead and show the step that's occurring here. So we, of course, have our lone pair of electrons on the nitrogen, comes over, forms a covalent bond to the carbonyl carbon. We've seen this step a bunch of times in the past couple of segments where we're looking at different addition reactions to aldehydes and ketones. So we'll go ahead and draw what would result from this, our tetrahedral intermediate. So we still have our 5-carbon chain there in place. Now we have a single bond to our oxygen. That oxygen has become an oxygen anion. And then our new bond I'll show in red here to our amine group, which I will also go ahead and show in red. So our nitrogen of the amine group is covalently bonded to the carbonyl carbon, or what was the carbonyl carbon. That nitrogen is directly bonded to a methyl group, and it's directly bonded to 2 hydrogen atoms. We'll go ahead and plug in our formal charge there. On the nitrogen, we're going to have a +1 formal charge, of course. And then carrying onward from here, as you might imagine, it's going to be pretty favorable for a proton to be lost from that nitrogen atom so that we can end up with a neutral intermediate, an intermediate with no formal charges on any of the atoms. So in order to accomplish that, we need to do a proton transfer here. And you'll notice that within this molecule, we have what we would call at this point a Zwitter ion. That's a molecule that has both a positive and negative formal charge within the same molecule. The term Zwitter ion comes up a lot in biochemistry with regard to amino acids, which occur in nature very commonly as Zwitter ions. So this particular intermediate we definitely refer to as a Zwitter ion because we have positively charged nitrogen, negatively charged oxygen. And so we have a couple of options here. One is that we could bring in a base to deprotonate our nitrogen. We could bring in an acid to protonate our oxygen, or we could do an intramolecular proton transfer here where we just take the existing extra proton here that's on the nitrogen and we grab that with our oxygen acting as the base. So that's what I'm going to do here in this case, but certainly this is not the only correct way to show this. The main thing is that you need to show that the oxygen is getting a proton from somewhere and the nitrogen is giving up a proton, and they could be donating protons to and from water, whatever else is available there as a source of proton donor and proton acceptor. So we'll go ahead and draw out the product of this second step of the mechanism where we had the proton transfer taking place. With the outcome of this proton transfer being certain that the molecule is going to be stabilized, because we now have a molecule that has no formal charges on it on any of the atoms. So we'll go ahead and plug in that proton that we just transferred in on the oxygen there in green. And we'll go ahead and try to color code this the same way that we did before with our nitrogen bonded to our methyl group. And now our nitrogen has just 1 bond to hydrogen, and our nitrogen is also going to have that lone pair of electrons derived from the covalent nitrogen-hydrogen bond, where those electrons now reside on the nitrogen. So at this point, the special name for this intermediate that we made, where we have our hydroxy group and our amine group geminal to one another, is referred to as a carbonyl amine. So I'll go ahead and write that down, that this type of intermediate is a carb enol. So the OL there will clue you in that you have an alcohol group present, and then the word amine, of course, cluing you in that you have an amine group present in that same molecule as well. So a carbenolamine, by definition, is going to be equal to a geminal alcohol amine molecule. The amine group and the alcohol bonded to the same carbon, hence it's geminal. So onward from there, we aren't quite done with this yet because we can continue onward to end up yielding a more favorable final product here out of this reaction. So coming onward from here, we said that the reaction is under slightly acidic conditions. And so what's going to happen here due to the fact that we're under slightly acidic conditions is that we're going to be able to protonate the hydroxy group in order to enable that to act as a leaving group here. So protonate the hydroxy group, because that hydroxy group, ultimately we're staging it to act as our leaving group. So I'm going to go ahead and show a proton here, and certainly since we're running this at, we said, a pH that was less than 7 up here in the reaction conditions, that certainly indicates to us that we do have some excess proton floating around in order to act as that proton donor here. So we'll show our arrow coming over to attack the proton, giving us our protonated intermediate, and this will enable us to have water set up as our leaving group here. So we'll end up with OH2 here with a lone pair of electrons and a positive formal charge. Over here on our nitrogen, we'll have our nitrogen bonded to our methyl group, bonded to our hydrogen, and then at this point, this is going to look really similar to when we were doing our addition reactions of nucleophiles under acidic conditions to form acetyl groups and things like that, where at this point water can act as our leaving group to end up yielding a resonance stabilized intermediate. And that's going to make this water leaving step particularly favorable, is the fact that we will create a resonance stabilized intermediate. As we've talked about time and time again, resonance is a really excellent factor for stabilizing intermediate. So water has broken away and left the building, and now we'll go ahead and draw out our intermediate that results from that. So we have our nitrogen, and that nitrogen, of course, has a lone pair, has a hydrogen, and a methyl group there. And at this point, for this particular resonance structure, we'd end up with a positive formal charge on the carbon. I'm going to go ahead and write water in as one of the products of this step. And of course, as we mentioned, there is resonance. It's going to go on here to stabilize that intermediate. So the actual intermediate is going to be the hybrid of the resonance structure that we drew on the left, and then following that green arrow that we just drew in, that's going to give us the resonance structure that is shown on the right. So we'll go ahead and show that pi bond there in blue, in green. And that's going to put the positive formal charge on the nitrogen. This second resonance structure that we just drew is going to be the most stable resonance structure because it is the one that has the octet fields for all of the atoms. And in addition, it also has maximized the number of covalent bonds. So after this occurs, we're almost to home plate here. Remember that we're trying to head toward an imine product because our starting material here up top was definitely a primary amine, an amine that has only one bond to an R group and has 2 bonds to hydrogen. So at this point now, we have one hydrogen atom left that's bonded there to the nitrogen. The nitrogen has a positive formal charge, so what we can do here to get rid of that positive formal charge and form our final imine product is a deprotonation step. So step 5 here, after that water leaving group is left, we're going to deprotonate to give us our final imine product. So we'll go ahead and show whatever we like here acting as our base. We just pretty much need a source of lone pair electrons to get this reaction to finalize. So certainly amines we recognize as being somewhat basic. So we'll go ahead and plug in our amine here to act as our base in this step, grabbing that proton from our intermediate there that's acting as the acid. The nitrogen and hydrogen bond breaks and those electrons go on to the nitrogen. That's going to lead us down the road to our imine. That molecule has that carbon-nitrogen double bond, and we're still going to have the methyl group bonded there. We're not going to break that carbon-nitrogen bond. We just broke the carbon-hydrogen bond here instead. So So it's going to leave us with our final product here, which certainly we would classify as an imine. And this is what's going to be the template always. If we start with a primary amine plus an aldehyde or ketone, we're going to end up with an imine product. And that imine product is always going to correspond, if you look at the overall effect here, it corresponds to replacing the carbonyl group of your starting material with a carbon-nitrogen double bond, where that nitrogen is bonded to whatever R group it had bonded to it originally. So in this case, the R group that was bonded to the nitrogen was a methyl group, as I'm circling here in yellow. And then in the final product, you end up with that methyl group still bonded to the nitrogen. You lose the hydrogens that were bonded there to the nitrogen during deprotonation steps, but you're going to retain that carbon-nitrogen bond in forming the amine product. So you'll have the carbon-nitrogen bond, or whatever the R group is there, and then you'll have that double bond to the carbon that originally was the carbonyl group. So that makes it relatively, hopefully, straightforward to predict these products without necessarily walking through the mechanism for this reaction every single time. And as I mentioned, it is possible with these reactions to use amines that are a little bit on the fancy side, that aren't necessarily what you picture as your prototypical primary amine, where you have a nitrogen directly bonded to one carbon atom, but instead permutations of that, where, for example, we have an R group that isn't an alkyl group. For example, we could have an R group that is a hydroxide group instead. So let's do an example of that just to highlight what I mean here about the flexibility of the nature of the R group that's bonded to our amine. So we're going to take benzaldehyde. It's our aromatic ring there, bonded to an aldehyde. And we're going to react that with hydroxyamine. So hydroxyamine is going to have H2N, hence the amine part of the name, and OH for the hydroxy part. So hydroxyamine. The hydroxy group here is going to function as the R group in this case. So this is getting back to the fact that this reaction is pretty flexible. As long as we have a nitrogen directly bonded to two hydrogens, we're going to have what we need in order for the imine formation to take place. And without going through the full mechanism for this, certainly we could go through the full mechanism, but we don't have to. I know your hearts are broken over that. But what we're going to do is just take our carbon-oxygen double bond, our carbonyl group in other words, and replace it with a carbon-nitrogen double bond. That nitrogen is derived from our hydroxyamine. And we're going to leave whatever the R group was that was on our nitrogen still intact there. So our R group we said was OH. We're going to plug that in. And that's going to be our final product of this particular reaction. So these are pretty flexible in terms of what the R groups can be, is what we're trying to illustrate here. Now let's go on and take a look at the formation of an enamine. And you will be hopefully pleased and somewhat relieved to know that this particular reaction is going to follow a mechanism that's very similar, initially at least, to the reaction mechanism that gave an imine product. The difference here is that we're going to be starting with a molecule that is a secondary amine. So we're not going to have two hydrogens directly bonded to the nitrogen of our starting material. Instead, we're just going to have one hydrogen that's able to be lost along the way. So that's going to impact the outcome of this reaction. So let's take a look at an example here of enamine formation, looking at the mechanism for this. We'll go through the first few steps of the mechanism here relatively quickly because we have seen this type of scenario before when we're looking at the imine formation. So what we'll do here is we'll take, just as our starting structure, acetone. Acetone is the common name for this ketone, a 3-carbon ketone. You could also call this 2-butanone. You should definitely take note of this name because this is more commonly used than the name 2-propanone. I think I misspoke just a moment ago and said 2-butanone. It's definitely 2-propanone here, more commonly called acetone, practically never called 2-propanone. So we're going to take acetone and we're going to react it with diethylamine. We'll get into the exact names of amines a little bit later on in the next chapter, but you should be able to dissect that diethylamine is certainly going to have two alpha groups directly bonded to the nitrogen. So let's go ahead and fill that in. Nitrogen We'll have one direct bond hydrogen there, and then it's going to have two amine groups, which we can show as two branches here. We could have just condensed this down and put CH2, CH3 in parentheses with a subscript 2 next to it. Either way, we have this right here, and we're going to go onward and take a look at what we would expect to happen here. So what we would expect to happen here is much like the mechanism for forming an imine, is that initially that nitrogen is going to act as a nucleophile and treating it like it is a base, since nitrogens are relatively basic. We're going to come over here and attack our carbonyl carbon. So our nitrogen is acting as the nucleophile there. And we're going to go ahead and form our intermediate here. And this step should, at this point, be looking very, very routine to you, because we've seen this nucleophile attacking the electrophilic carbonyl in nearly every reaction we've looked at related to aldehydes and ketones thus far. So a new bond between carbon and nitrogen there, and that nitrogen is going to have our hydrogen directly bonded to it. It's going to have also those two ethyl groups directly bonded there as well. We'll go ahead and plug our formal charge in there on the nitrogen. And then at this point, we would describe this step. If you're one of those that likes to describe these things in words, step one of the mechanism was that the nucleophile, that was our nitrogen atom in particular, of our amine, attacks the electrophilic carbonyl carbon. All right, onward to step two. Step two, also very analogous to our imine formation reaction. And at this point, we have a nitrogen with a positive formal charge, and it's got that proton on it. We can just pluck that proton off to give us an intermediate here that has no formal charge on the nitrogen. Likewise, the oxygen anion needs to pick up a proton there, so we can do a proton transfer here. This can occur intramolecularly, which we're going to show in the mechanism that I'm writing. You can also show this proton transfer occurring by having these attack any outside source of proton donor or proton acceptor here. So we get our acid-base chemistry going on here, picking up the proton from the nitrogen, transferring that onto the oxygen, and that's going to give us our intermediate here. So that brings us to our intermediates, and we'll go ahead and draw that all in. Still have our two ethyl groups directly bonded to the nitrogen. And our oxygen here should now be a hydroxy group rather than an oxygen anion, since we picked up a proton. We have all that in place for our intermediate here. And then at this point, what we need to do, also continuing onward, much like we did with the imine formation reaction, is we're going to protonate that hydroxy group with the available acid. This reaction, much like the other one, is run under slightly acidic conditions, so we have a little bit of acid there to carry out the protonation step. So in step 3 here, just like for the amine formation, we protonate the hydroxy group, and the purpose of this is going to be to create a better leaving group. So oxygen comes over, acts as our nucleophile, of course, to give us our intermediate here, with now our water staged as a leaving group. So we go ahead here, protonate, and we're going to write in the intermediate that results from that particular step. All right, so now at this point, what we've drawn in as a result of that protonation step is we've got our water set as the leaving group, so now the water is going to break away, just like what we saw with the amine formation reaction. So it protonates, that creates a really good water leaving group, then the leaving group leaves. And that's going to create a resonance stabilized intermediate here, much like what we saw in the previous examples of forming the imine. So we'll go ahead and draw out our resulting intermediate here. And we can show how that's going to be stabilized by resonance, because we have that nitrogen, which has a lone pair of electrons. It's adjacent to a carbocation. Anytime you have a lone pair adjacent to a carbocation, resonance is going to be something to be on the lookout for, because that's certainly going to be a stabilizing factor there. All right, so we'll go ahead and draw in our pi bond there in red. Go ahead and copy over my nitrogen, and go ahead and copy over my two alkyl groups. Okay, and we'll have that positive formal charge on the nitrogen. Now, if you think back to what was going on in the imine formation mechanism, at this point what happened was that there was a nitrogen-hydrogen bond, and that nitrogen-hydrogen bond we lost the proton from to lead us to our final imine product. We can't do that here because we don't have a nitrogen-hydrogen bond available. That's because we started with a secondary amine rather than starting with a primary amine. So we only had one nitrogen-hydrogen bond to start with. We already lost that earlier. So we have no more nitrogen-hydrogen bonds to work with here. And so instead, the reaction is going to have to take an alternative pathway here to get to our final product. And that alternative pathway is going to be what we would think of as an elimination reaction. So we've yielded here our intermediate with our nitrogen cation. And now what's going to happen is that we are going to carry out an elimination reaction. And we can show that happening here on our second resonance structure. We'll do an elimination. And this is what's going to yield the alkene final product. We've seen E2 and E1 reactions in the past that yielded alkene groups. The same is going to be true here, that we're going to end up with an alkene group by removing a proton from either this carbon atom or the one over here. So one of those two carbons that I put a star on, we're going to be losing a proton from, and the carbon-hydrogen covalent bond electrons are going to come over to enable us to form the alkene group. So in this case, both of our starred carbons are equally substituted carbons. So it doesn't matter which one of those you choose to remove the proton from. We're going to do an example later on where you will have to follow Zaitsev's rule to make the more stable alkene product out of this reaction. But for now, it doesn't matter which one of these two you choose in this elimination reaction. So in the elimination reaction, we're going to use water as our base here to grab that proton. And water is not a particularly strong base, which this implies to us that this reaction is a pretty happy, ready to go reaction. So we have a relatively weak base able to come in and just grab that proton there. The electrons from the carbon-hydrogen bond come over to make our alkene group, and then to avoid going over the octet, of course, that means that pi bond from the carbon-nitrogen bond has to go up onto the nitrogen. That's going to make everyone happy overall, because now our nitrogen also has a complete octet and no longer has a formal charge. So we'll go ahead and draw out the product that will result from this, the enamine. So plugging everything in here now, we have a carbon-carbon double bond. We now just have a CH2 group there on the end, so good news, we're avoiding going over the octet rule. Nitrogen's going to have a lone pair because we took the pi bond and moved that up onto the nitrogen. That nitrogen's also going to still be bonded to those two ethyl groups. We're not going to break the carbon-nitrogen bond ever. In this mechanism, we're just breaking nitrogen-hydrogen bonds, which are much easier to break, ready to go and leave. So at our final conclusion here, we've created our enamine product. Now, as I mentioned, sometimes you will run into situations where rather than having a situation where the carbon atom that's double bonded to the nitrogen is equally substituted on both sides, for instance here where we have the two methyl groups that I'm highlighting in yellow, Instead, you could have a situation where you have two different groups bonded there, and we need to determine how we're going to decide which of the protons to remove in order to create our final product. So let's take a look at an example here of an asymmetrically substituted ketone starting material or aldehyde starting material, whichever we like here. So we're going to start with a ketone that is asymmetrically substituted. So we'll start with 2-butanone for an example here. So we've drawn out the structure of 2-butanone. And we're going to also start with dimethylamine. So dimethylamine, of course, going to have our 2 CH3 groups and our nitrogen directly bonded to 1 hydrogen. And we're going to ask what the product of this reaction would be. So I'm not going to go through the entire mechanism again, since we just did that, and you should be able to walk through that mechanism if you needed to. But what I am going to draw is the last intermediate before we get to our final product. So we can take a look at the possibilities for elimination reactions at step 5 of the mechanism. So step 5 is that step if we look back here at the top of the slide. That's this step. So we're going to be looking at that intermediate that leads into the elimination reaction. So we're going to draw up what that intermediate would correspond to. And again, if you had to, you could write out the mechanism for this, but I'm just going to write out the structure of this intermediate. So our intermediate structure going to correspond to replacing the carbon-oxygen bond there with a carbon-nitrogen double bond. So we'll go ahead and write everything in here. So we've got our carbon-nitrogen double bond that I filled in, and that nitrogen is going to be still bonded to the 2 alkyl groups, so our 2 CH3 groups. That nitrogen, as a consequence of that, is going to have our positive formal charge. So that's our intermediate that leads into the elimination step in this particular reaction. So now what we need to do is we need to decide where we are going to deprotonate. So we have our groups that are candidates for this are going to be either set of protons that are on the carbons adjacent to the carbonyl carbon. So that's going to be the sets that I've highlighted in red there. So there's going to be 2 possible products resulting from this. Those 2 possible products are going to correspond to deprotonating at either of those 2 carbons that we see in our structure there. So the 2 possible products corresponding to our 2 possible deprotonation locations are going to correspond to removing the proton here on the right. So I'm just drawing that in here to show that deprotonation step. So we could have deprotonation occurring there, and our deprotonating agent can be water or whatever else we have there as a source of lone pair electrons. So comes in, grabs that proton, carbon-hydrogen bond breaks, comes over, and that forces the electrons from the pi bond up onto the nitrogen, giving us our enamine that would result from deprotonating on that carbon atom on the right here, the one that I circled just now. So we'll go ahead and draw out our enamine product. We've got our carbon-carbon double bond there, CH2 group at the terminal. Now our single bond to our nitrogen, and that nitrogen is directly bonded to 2 methyl groups, which I'm going to put in brackets this time to save a little bit of space. So that's option 1. Option number 2 is that instead of deprotonating there, we can do the same thing on that proton that's on the left. So if we do that, what we're going to end up with as a result of option 2, and I won't draw out the mechanism for this particular step, but that's something you should be able to fill in if you need to, is using this same process that we were using right here that I'm circling in yellow to work on that CH2 over here on the left. So the final product that would result from deprotonating there on the left is going to correspond to having that CH3 group still in the end. That CH3 group is going to be directly bonded to the carbon that's underlined in yellow. That carbon that's underlined in yellow will have lost one of its two protons. The second one will still be there. And due to the loss of that second proton, we're going to have our alkene group form. And our carbon now is still bonded up top to the N-dimethyl, like so. So we have to ask ourselves here, which of these two products is going to be the preferred product, or does this form randomly? Is there no preference for one or the other? So this is where we think back to Zaitsev's rule to predict the major product of this elimination type reaction. Zaitsev's rule, as a reminder, says that if we have the opportunity to form two or more constitutional alkenes, the favored alkene is going to be the most substituted one. So Zaitsev's rule says form the most highly substituted, most alkyl substituted alkene. So we're asking which of these two alkenes has the most alkyl groups directly bonded to the alkene. So we take a look at our alkene in each of the two cases, so alkene here versus alkene here, and we count how many alkyl groups are directly bonded to each one of those. Down here at the bottom, we end up seeing that there are 2 alkyl groups directly bonded to our alkene. Up top, we see that there's only one alkyl group directly bonded to the alkene, that ethyl group, because over here it's just hydrogen atoms rather than alkyl groups. So the option on bottom here is your more substituted alkene, and therefore that's going to be the major product of this reaction. So if you're asked to predict the major product of the reaction, certainly it's going to be the one on bottom here, because that is the more substituted product. So Zaitsev's rule, definitely an important thing to keep in mind here as you're thinking about products of these enamine formation reactions.